Hi, everyone, and welcome to Tech Tuesday. As we wait for everyone to jump on here, I'll give a brief introduction. I'm Abby Weber, and I'll be your host today. I work on the marketing team here at Blue Ring Stencils, and for today's webinar, we are excited to be featuring a presentation put together by Greg Smith, Manager of Stencil Technology for Blue Ring Stencils. Today's topic is mitigating intermittent failures from head-on pillow and other defects through stencil design. Today's webinar will be recorded and will be available to you through a link that you'll get in your email tomorrow. There will be time for a Q&A session towards the end. You'll see a Q&A tab at the bottom of your screen, so feel free to throw any questions you have in there. If we don't get to your question today, we will be sure to follow up, or you are always welcome to contact us directly. Now let's jump right in.
Hello everyone, and thank you for your time. Today I'll be sharing some information on mitigating head-on pillow and other defects through stencil design. I want to start this discussion with a review of what head-on pillow is. Then we'll move to how it's formed and the causes, and then we'll get into what we can do from a stencil design to help or reduce or eliminate these head-on pillow and other assembly defects. And then finally we'll wrap up with some conclusions. Let me start by saying that there are a lot of folks in the industry that are much more educated and informed than I am on the subject. I study it because customers come to us for solutions, and I feel it's extremely important to understand these challenges before we can address the solutions. So you'll see me quoting research in this presentation as I review what head-on pillow is and its possible causes. I do want to share one definition with you that I really like. Head-on pillow is characterized by complete melting of both the solder paste and the BGA solder ball, but without insufficient coalescence to produce a well-formed solder joint. These images show an example of the head-on pillow challenge. This defect is referred to by several different names: head-on pillow, head-in pillow, ball and cup, ball and socket, and hidden pillow. I typically call it head-in pillow. When you hear these different terms, don't be alarmed. They're all talking about the phenomenon where the joint is made up of two distinct masses formed by the BGA balls and reflowed solder with incomplete or no coalescence. So looking at this image, you can see the reflowed solder paste at the bottom, and you can see that the BGA ball at the top collapsed but didn't coalesce into one mass of solder. There is physical contact here, so in-circuit testing may look good, but over time, this contact may separate and then field failures can occur. So let's look for a few minutes about how this defect is formed. This pictorial describes the different. More importantly, it shows how the gap is created between the ball and the solder paste due to the dynamic warpage of the package or the PCB. And if there's not enough flux to remove the oxide coating on the surface of the ball, or contamination present on the solder ball or in the molten solder paste, these two masses just will not coalesce, and this head-in pillow defect will result. I want to make sure everyone understands that the solder paste deposit is controlled primarily by the stencil, and to some extent the printer settings, and the activity and the amount of flux in the solder paste is controlled by the paste manufacturer. So the stencil design is key in determining the solder paste volume the head-in pillow defect. One way to gain more volume without narrowing the gap between apertures is to use square apertures when printing BGAs. You can see in figure 5, shown here, when looking at the volume of cubic mils deposit. I want to show this in a different way using this chart. On the left, I've shown 4 different sizes of round apertures that might be present on BGAs to make a point. In the next column, I've calculated the volume in cubic mils based on a 4 mil thick stencil. So you can see the volume of the round aperture in the second column and the volume of the same size square aperture in the fourth column. So as an example, the 15 mil round aperture would theoretically deposit 707 cubic mils of paste onto the PCB, and a 15 mil square aperture would deposit 886 cubic mils of solder paste. So just changing the shape from round to square in this case increased the solder paste volume by 25%, and without narrowing the gap between apertures. So there's no added concern of bridging. I do want to quickly discuss the layout of the BGAs here. When the BGAs are aligned in rows and columns, shown on the left image here, and are evenly spaced, changing the shape from round to rounded square is the easiest way to add volume. When the rows and columns are offset, shown in the right image of this slide, the square pads will need to be rotated 45 degrees, creating a diamond shape aperture. This maintains an even gap between the apertures and will prevent shorts if the minimum gap is maintained. One way to define the minimum gap between apertures is to use the 1.5 times the foil thickness rule. This rule states that at a minimum, there must be 1.5 times the foil thickness of metal between any two apertures on the stencil. As long as good gasketing is maintained, this rule seems to be very successful at preventing bridges. The important concept to remember on these last couple of slides is that by simply changing the shape from round to square, we can increase the volume. You'll see how this can help reduce or eliminate head and pillow on upcoming slides. I want to stress here that just changing the stencil design is not a magic bullet to eliminate all head and pillow defects. This challenge is very complex and there can be many different contributors. In fact, many times, minor tweaks in 2 or more of these variables are required to eliminate head and pillow defects. So I wouldn't be doing my job if I didn't briefly discuss other areas that should be addressed when addressing head and pillow. These include component misplacement, which can be a key contributor. The reflow profile is also critical when addressing this defect. And we see a lot of customers focusing on both stencil design and reflow profile when addressing this issue. Contamination on the BGA balls or even of the solder paste itself can also be a contributor. And of course, there are many variables in the actual solder paste being used. And some solder paste may reduce this defect, while some do not based on the flux activity. Solder ball oxidation levels can also play a part, as well as the manufacturing processes of the BGAs themselves. All these areas should be addressed when working on a root cause evaluation of this head and pillow defect. Something else to remember is that these longer and hotter reflow profiles associated with lead-free solders also make this challenge more prevalent. And in some cases, lower temperature solder alloys can be used to address this issue. One variable I do want to emphasize is the dynamic warpage that occurs in BGAs during the high temperature reflow process, especially with lead-free alloys. The main cause here is the coefficient of thermal expansion mismatch between the substrate and the silicon. When this occurs, the solder balls in the component corners are lifted up from the solder paste on the board. Separation of the BGA balls from the solder paste allows oxides to form on the solder balls since they're no longer touching the solder paste that holds the flux. So when the package flattens out during the cool down process, flux content in the solder paste is not enough to overcome the oxide formation of the BGA balls, and that prevents the molten metals from coalescing during the cool down process. A few other failure modes noted in this research are solder ball true position, which would be a result of component manufacturing, the PCB board design itself in relation to heat dissipation, and package standoff. Again, all these failure modes should be addressed when trying to resolve the root cause of the head and pillow challenge. Thinner materials and finer ball pitches all contribute to this assembly challenge, and there's no end in sight as thinner, more powerful mobile devices and the need for reliable package-on-package assembly continues. These are just some of the drivers that create this defect type that continues to challenge our industry. So let's discuss some stencil modifications for head-on pillow mitigation. As we've discussed, one of the easiest solutions is to modify the stencil aperture design. This process can be done quickly and is relatively inexpensive, and the stencil can be replaced in a day or so if needed. In many instances, the head and pillow defect may not be expected, and a new stencil may be required to address and possibly correct the defect quickly. The most common stencil solution is to overprint land pads in the corners as shown in this example. In fact, I've seen many component drawings for BGA type devices that recommend larger stencil apertures in the corners like is shown here. Please remember it's critical to share the component drawings with the stencil manufacturer if the PCB design doesn't include the modifications. In addition, and I say this all the time in these types of presentations, if you only share the paste Gerber layer with your stencil house, they can do very little to proactively design your stencils. It's important to understand the more information you provide at your stencil order, the better the design can be. Now let's talk about the actual solder paste deposit. It's widely agreed on that solder paste is approximately 50% metals and 50% flux. So after reflow, the solder deposit height will be roughly half the solder paste deposit height, as shown here. So you can see I've shown a 4 mil solder paste deposit, and the metal height after reflow will be approximately 2 mils. Now let's look at a chart similar to what I presented a few minutes ago, and I want to show you how minor overprints can affect the total volume. The first 4 columns in this chart are the same as what we looked at earlier, showing approximately a 25% increase in volume when you change an aperture from round to square. The 5th and 6th columns here show how adding 1 mil to the size of the square aperture affects deposited volume. Again, I always use a corner radius when I'm creating these square apertures. So in these examples, I used a 2 mil radius, and the volumes shown are the result of the radius design. So you can see adding just half a mil per side to these apertures can increase the volume versus the original round pad by 42 to 54%. And if we add 1 mil per side to the aperture, or 2 mils in the X and the Y, we add 59 to 92% more volume to the paste deposit. So this is a very useful tool when working to eliminate head and pillow defects. Now I want to show a better visual here when discussing paste height. Like we said earlier, when we print a round aperture 4 mils high, 1:1 with copper, we can expect a 2 mil solder deposit after reflow. When we change that shape to square, then we get approximately 25% more volume. So how does that affect paste height? I've not studied exactly what the solder paste deposit looks like during reflow as the overprint pulls back into the copper pad, but here's what we can expect physically after reflow. If we deposit 25% more solder paste, the net solder height after reflow would be half of that, or 12.5%. So during reflow, the solder paste deposited off of the copper land pad will pull back to the copper pad. And as that paste pulls back, the overall height of the solder paste increases. Then the volatiles will burn off and dissipate, and the resulting solder metallization would be 12.5% higher, or in the case of a 4 mil print foil, an additional 0.25 mils will be added to the deposit height just by changing the aperture shape from round to square. When we change the shape to square and also increase the aperture size by 1 or 2 mils, we see a significant increase in paste height after reflow. I just picked the 15 mil round pad we showed earlier in our volume chart as an example to look at here. When we change the 15 mil round aperture to square, we get an additional 1/4 mil in height. If we oversize the aperture a 1/2 mil per side, we get a solder height increase of 0.86 mils. And if we increase the aperture size from a 15 mil square to a 17 mil square, only 1 mil larger per side, or 2 mils in the X and the Y, we get 62% more solder volume and an additional 1.24 mils in reflowed solder height. That's a 31% increase in solder height after reflow. And as paste is transitioning to liquid during reflow, I believe that the pullback height is even more, which helps maintain contact with the BGA sphere during reflow, preventing the head and pillow defect. So I want to introduce a video here. I want to be able to show what paste looks like during reflow when it's printed onto the solder mask beyond the copper land pad. Many customers are rightly concerned about possible solder balls or shorts with this overprint concept, so we made this video. We use a no-clean Type 4 SAC 305 solder paste. We overprinted the copper land pad 600%, and the overprint aperture is 118 mils in diameter. The copper land pad is 19.68 mils or 0.5 millimeters, and we overprinted onto the solder mask 46 mils. So you can see here that the flux is activated during the initial reflow stages, and the solder spheres and the paste start pulling together. Then you can see the flux become active. The deposit almost looks drier. Then the solder becomes liquid and pulls in quickly to the copper land pad. Finally, you can see the outgassing and the volatiles burning off. This is what happens when we overprint, even at much smaller percentages. Paste pulls in, increases the contact height, then reflows and freezes. You can also see at the end of the video there are no solder balls left in the flux ring. This is dependent on the type of solder paste you are using. I've definitely seen some solder paste create solder splatters or solder balls more than others, so you also have to consider the solder paste being used. Okay, so here's a visual showing the 600% overprint and the deposit after reflow. You can see we calculated the theoretical height of the reflow solder deposit here. This shows theoretically that we were able to double the deposit height by overprinting and allowing the solder paste to pull back to copper during reflow. This overprint solution has been used for years with bottom terminated component I/O pads to apply additional volume to the toes of these pads. We've also recently seen where overprinting the toe of I/O pads on bottom terminated components can decrease voiding in the bottom terminated components ground pads, but that's a topic for a different discussion. Here's a depiction of what an overprint design in the corner of a BGA component might look like. You can see we've created square apertures with an overprint of 1 mil per side in these corner apertures to make sure we have enough solder paste and therefore solder flux to maintain contact with the BGA balls during the reflow process. Another method of adjusting volume to the PCB land pads during the print process is using step stencils. In many cases, we can step the areas around the BGAs thicker or thinner depending on the application. So for example, if we have a base foil of 5 mils for large components, but there are 0.4 millimeter pitch micro BGAs present that should be printed on a 4 mil foil, we can step down this area to 4 mils to deposit the correct height and volume of solder paste for that component. This type of stencil is typically referred to as a step-down stencil. The other type of stencil is what we call a step-up stencil. If we have a base foil of 4 mils with a lot of O201s or 0.4 millimeter pitch BGAs and have a large LGA, we can create a step up in the LGA area to the component manufacturer's recommended 5 mils thick. The step up stencil allows us to increase the thickness of the foil at specific locations as shown here. So what technologies are used to make these step stencils? There are 3 primary methods used in North America, and I want to briefly go over each of these so that you understand the differences in these technologies. Chemical etching is the oldest technology in use today. A photographic process is used much like etching circuit boards. Photoimageable resist is applied over the stainless steel to mask the surface everywhere except for where the foil needs to be thinner. The foil is then run through an etching machine where an acid is sprayed on the stainless steel and dissolves the metal to reduce the foil thickness. This process uses hazardous materials and creates hazardous waste and is the least accurate technology available to produce step stencils. The biggest concern I have with using the chem etch process is the satin or semi-rough type surface finish it produces. And you can see that here in that right picture just above the words etched technology. I've seen in so many cases where flux is left behind on the etched surface of step stencils and always wonder how much flux is being robbed by the surface of the stencil. Laser welding technology is utilized for the largest percentage of step stencils in North America today. These lasers are extremely accurate, and the foil being welded is very accurate as well. I would estimate that 90 to 95% of the step stencils our company produces are welded steps. So how does this work? If the base foil is 5 mils and there's a requirement for a 4 mil step down, we take a 5 mil foil, laser cut out the area that should be 4 mils, then we cut out a piece of 4 mil foil exactly the size we need, and then we vacuum those two pieces together and then weld. You can see the welded bead in the upper right corner of the screen. The limitations we currently have when welding steps using this technology is 3 mils thick. So right now we can't weld foil less than 3 mils thick. The last technology I want to discuss for step stencils is a fairly new technology in North America. This micro machining process is produced by specialized milling machines capable of removing stainless steel very accurately. We can machine step depths with micron accuracies. For example, we could machine a depth of 0.6 mils or 15 microns in a 3 mil foil, creating a foil thickness of 3 mils in some locations and 2.4 mils in others. This technology allows us to machine foils down to 2 mils thick, and we're hoping even thinner as our research continues. Back in 2017, I worked with Chris Shea on a paper for SMTAI. We compared laser welded versus machined 1 and 2 mil step down stencils to see what differences there were in the two technologies. What we found was we could get acceptable print deposits with a laser welded step when the closest edge of the aperture was 25 mils or greater than the edge of the step. We call this the keep out zone. And with micro machined steps, we could get the same results with only a 10 mil keep out zone. So both of these technologies provide great results, but when needed, the micro machining process could be used when the keep out zone is down to 10 mils, providing more options when designing stencils in this world of miniaturization. So let's get back to our head and pillow topic. Let me take what we just went over and apply it here. Again, if we can eliminate the gap created when this dynamic warpage occurs during the reflow, we may be able to prevent head and pillow defects. Instead of, or in addition to overprinting the corner pads, we could have a step-up area, and this would allow us to create additional paste height and volume and not rely solely on paste height increase from overprint. Let's use the image shown here as an example. If we want this pink area to be 5 mils and the rest of the stencil to be 4, we would need to measure the distance between those apertures and apply the dimension to the keep out zone to decide which step technology can be used. In the example here, there's not enough keep out to use a welded step, so we would need to use a micro machine process. We would machine the entire stencil surface down 1 mil, leaving these corner areas, shown in pink, 5 mils thick. When printing, the deposits in the pink area shown here would be 5 mils tall, and the rest of the deposits would be 4 mils tall. This is just another method we can use to approach this head and pillow defect. Our company is currently doing a lot of R&D on improving this micro milling technology, and I feel strongly it'll be a key technology to address new challenges as emerging technologies continue to be introduced to our industry. Okay, so that wraps up our discussion on head and pillow, and I want to spend my last few minutes discussing other stencil strategies we can use to address specific defects. The first of these is solder balls or mid-chip beading. Mostly we see this concern with no clean solder paste assemblies. So when a customer calls and says they're experiencing mid-chip beading, I first get the reference locations from them, and then I identify the packages that we're dealing with. So in this case, we'll deal with an 0201. Then I physically lay out the package outline and the leads of the part itself in Gerber. Here I've done that in this yellow line. Now when you turn on the copper, mask, and paste layers, you can overlay the actual part layout to see how the part theoretically sits in the solder paste. On 2-pin parts, I like to see the component extents about midway into each solder deposit. So in this example, you can see the part is sitting a little further out than the midpoint, and more solder paste is under the part than I normally would like to see. Now we can start replacing the current paste layer apertures with apertures created for this defect. I prefer to use the U shape as it removes solder paste from the inside center of the paste deposit. Typically, mid-chip beads or solder balls are created when the part is placed into the solder paste and the solder paste is squeezed up under the inside center of the part. As the board and the part pass through reflow, this squeeze out then reflows and pulls to the side, creating the solder ball. So this design has been very successful through the years in reducing or eliminating these types of solder balls. Other designs, such as the inverted home plate, have also been successful in solder ball mitigation. I would say overall, I've had the least success with the standard home plate, although I know many of our customers still use that design. I want to spend a minute talking about tombstones. Typically, we've seen removing paste from the toe or the outside of the 2-pin part land pads reduces or eliminates this defect. One way to do this is with the rotated U shape, as shown in this image. The thought process here is as the solder paste goes liquid, it wants to wet to the unprinted copper of the land pad. When we remove solder paste from the outside of the pads during reflow, the solder paste wets or flows away from the center to the unprinted area on both sides and keeps the part centered as the paste liquefies and then freezes. In the case of very large pads where there is a lot of exposed solder beyond the part leads, for example, an 0402 placed on an 0603 pad set, more of the aperture may need to be removed from the outside to create a larger area of copper with no solder paste present. In some cases, I've removed 1/3 of the outside of the aperture when addressing tombstones. The concept here is simple. Lay out the component in Gerber, overlay it to the copper and mask layers to visualize what is happening. Just going through this process allows for creating problem solving and helps me address these types of issues for our customers. And it's actually something that customers can do on their own. Another challenge that comes up from time to time is bridging after reflow. In this case, the board is printed, passes SPI, then fails AOI post-reflow. What we think is happening when this occurs is that during reflow, the lead is exposed to the convective heat of the oven, causing solder just around the foot to wick up the lead. Once the liquid solder gets to the shoulder, there's nowhere else for it to go, so it starts pooling at the foot of that lead. And when this occurs on two adjoining leads, then those pools can touch and create shorts. So we typically see this happening when the foot is 25% shorter or more than the copper land pad. The way we can address this issue is to create a ratio of the foot length to the length of the copper land and then reduce the volume based on that ratio. So if the foot length is 75% of the land pad, we reduce the volume 10%. If it's 26 to 50%, we reduce the volume 25%. And if it's 25% or less, we reduce the volume by 40%. Again, this has solved this bridging issue many times through the years for customers. So let's move on to the subject of many research papers and long discussions on the phone with customers, voiding. Again, like many of these defects, the solutions to voiding are multifaceted, and just the stencil alone doesn't always solve the voiding challenge. But I want to take a few minutes and address some of the research we've done through the years. I'd like to emphasize with this first slide that we've studied many different designs to identify the best design to minimize voiding on ground planes, mostly bottom terminated components. We've been able to prove the window pane design produces less voids than the 5-dot pattern shown here, so I don't recommend that design. I also like to always point out that the IPC 7525B standard suggests a 25 to 50% reduction in area. So a 50 to 80% coverage is what is recommended in the spec, and I definitely agree with those numbers. Another thing we've learned through our research is that 60 to 70% coverage or a 30 to 40% reduction seems to create the lowest percentage of voids without causing float and skew. So you can see from these images that we presented at SMTAI that as the coverage decreases, voiding increased. In this paper, we also looked at the use of a lot of different panes in one pattern, very wide webs in one pattern, and then very large perimeters in another pattern, while maintaining a specific percent area of coverage. So we looked at 4 different designs just using a window pane. We found that our standard web design, keeping close to 10% of the perimeter free of solder paste while targeting 60 to 70% coverage, produced the least amount of voids. Now sometimes that standard window pane void percentage is just not low enough for your customer. So from a stencil design, we wanted to understand what else we could do. So last year we presented a paper that explored the relationship of overprinting the toe of the I/O pads to the voiding percentage of the ground pad. And what we found is that by overprinting the toe as much as 20 mils, we could reduce the overall voiding percent. The theory behind this data is that as the overprinted paste pulls into the copper I/O pad, it tends to lift the part slightly, allowing gases or volatiles to escape from underneath the part. Then as the solder freezes, the part is drawn down and flat. I just know that we were able to see this in our data, and there was another paper presented at the same conference showing those same results. So this is another tool in our belt when we have to really work with customers to reduce voiding on bottom terminated components. Okay, so let's recap. Head and pillow or head-on pillow, along with these other names, all refer to the phenomenon where the 2 metal masses, the BGA ball and the solder, do not reflow together and coalesce into one solid metal mass during reflow. The gap between the solder paste and the BGA sphere is the root cause of the defect, and increasing the solder paste height, making sure there's always flux present throughout the reflow process, will prevent head and pillow. And using a rounded square and or overprinting will also contribute to adding more volume and height during the reflow process. Finally, using the micromachining process to create step-up stencils may be another alternative in gaining additional volume and height during the reflow process, which will prevent this defect from occurring. Then we addressed mid-chip beading and discussed removing paste from the inside center of the pads and how that could reduce solder balls or mid-chip beading on the stencil design, especially when no clean pastes were being used. Finally, we talked about tombstone defects and how they could be improved by removing solder paste from the outside of the component. And one way we can do that is with the use of a rotated U-shape or rotated inverted home plate. And in some cases, you may have to just remove solder paste from the back side of those pads if it's a very large pad and you're replacing a smaller part on it. Then we looked at bridging and how bridging occurs after reflow but not after print, what we can do and what we can look for to try to resolve that defect. And finally, we talked about voiding. Voiding in component ground planes can be reduced through stencil design. We've got to optimize the percent coverage. We've got to get as much solder paste volume as we can without causing float and skew, but we also don't want to print too close to the edge of that copper ground plane. So we don't want to get any solder splatter or solder balls happening in there between the ground plane and the I/O pads. And all these have shown that we can reduce voids, and these are just tools in our tool belt that we can use when we need to. So here's my contact information, and again, thank you for your time. I hope you've learned or thought about something new during this presentation, and please let me know if there's any other questions I can help with. Thank you.
Awesome presentation, Greg. Now let's open up the floor for questions. Dave asks, do U-shaped stencil apertures cause any release issues?
No, I mean, we have to always, whenever we apply a specific design, like in this case, like you're saying, a U-shape, we always have to still look at the area ratio. So as long as we maintain area ratios, you know, if it's an uncoated stencil above 0.6, then we should be good. But especially, if you want to start applying a U-shaped aperture to like an 0201 type component, then yeah, it becomes really critical to maintain the area ratio in that printability area.
Great. When manufacturing a step stencil using the laser process, is additional filler metal added to the weld bead? Can very small step-up features be created from the weld bead alone?
So no, we don't add any. So there is no there's no additional metal added. So the laser is just melting the two materials together, the thinner foil and the thicker foil, and creating that bead. So there's no added metal. I believe so. We are limited to size of the weld. I believe around, and I could be wrong here. I have to check with our manufacturing guys, but I believe it's around 100 mils or larger. We can physically, pull down together on the vacuum to weld. But I could be wrong. It could be somewhat bigger than that, but it's still pretty small.
Okay. Is a reverse home plate different than an inverted home plate?
Yes. So an inverted home plate is typically referred to as a like the reverse of a standard home plate. So it would have like the V cut out on the inside edge of the aperture. And then if you take that and you rotate it 180 degrees so that you would take away material from the outside of the component, that would be kind of an application for like if you were trying to address tombstones. So with tombstones, you want to remove metal from the outside edge of the component, and solder balls, you want to try to remove solder paste from the inside center of the component. So really, one is just a rotated 180 degree version of the other.
All right. When step down process, what is the squeegee's requirements, metal or rubber?
No, typically, I would say most customers are using metal, just standard metal squeegee blades for doing a 1 or a 2 mil step down with no problem. And so that's why when I was talking about that keep out zone is to allow the squeegee to conform, down in that step down area, to conform down off of the higher area down into the lower area. And so you can imagine there's an area that where that squeegee is bending or kind of conforming down into the pocket, and that's what that keep out zone kind of refers to. How much room do you need? And so with a welded step, 1 or 2 mils, we could typically get by with a 25 mil minimum keep out. Whereas if we go to a machine step, we can typically go down as close to 10 mils.
Awesome, thank you. For step stencils, can the keep out dimension be affected by the mechanical properties of the application blade?
Read that one more time so I can think about it.
Sure. For stepped stencils, can the keep out dimension be affected by the mechanical properties of the application blade?
I guess maybe that what we're talking about is if we applied more downward pressure, would it help that squeegee conform down into the pocket maybe quicker? I would say no. I would say that if you start applying excessive pressure, to a welded step, you're just going to start coining the stencil foil faster and cause other issues. So I think it would be better to just maintain your standard kind of blade tension and speed settings. I know in some cases customers will slow the squeegee speed down when they are going to go down into a pocket, a step down area, just to allow more time for those apertures to fill. But pressure, I wouldn't think would change much. You still want just the minimum pressure so that once that squeegee bends down to that, or goes down, transitions down to that pocket, you just, whatever the least amount of pressure it takes just to get a good clean wipe of the solder paste.
Gotcha. Let's see here. So in regards to nanoslick for stencils, how does it help reduce stencil issues?
So nanoslick, the NanoSlick product does two, maybe three primary things. The first thing it does is if there's any squeeze out between the stencil and the PCB. So if there's any squeeze out, an uncoated stencil would allow the solder paste that squeezed in between the two. When the board separates from the stencil, the solder paste could technically or would most likely stick to the bottom of the stencil, which will make the next print, the gasket will be even worse. So the NanoSlick prevents the solder paste from sticking to the bottom of the stencil, makes it easier to clean the stencil. That's kind of a byproduct of that. The other thing that NanoSlick does is it helps solder paste release from the apertures. So if you're concentrating on area ratio apertures and I would say the 0.5 to 0.6 area ratio range, so lower than the what you would want with an uncoated stencil, the NanoSlick will give you 25% or so more release than an uncoated stencil would on very small area ratio apertures. And then probably the most benefit that I've seen even recently, we're going to present a paper at SMTAI in a few weeks. We're looking at 2 and 3 mil foils, really small apertures, so print to fail apertures down to 3 mil diameter. But another big reason to use NanoSlick is just for the print variation. So with NanoSlick, we see the coefficient of variation or the variation in the print process reduced significantly versus an uncoated stencil. So with the coating, you can reduce the overall variation in the print process. Make the print from board to board, print to print will be more consistent, and you can get better transfer efficiency and more consistent transfer efficiency.
Awesome. Thanks for explaining that. Does the etch process of a step-down stencil etch the sides of the apertures as well as the surface?
No. So typically the step process is done before you cut the apertures. Whether you're etching a pocket, reducing the material thickness from 4 mils down to 3 mils in an area using the etch process or a machining process, or even the welding process, all those processes are done before the actual apertures are cut. But what I was trying to say in the video was that the etching process produces that kind of semi-rough surface. And so as the squeegee is pulling solder paste across that surface, what I see is it looks like a lot of flux is left behind. So the squeegee will squeegee up, all the solder spheres and get a good clean wipe of the solder paste, but you can still see that there's flux left behind in that porous surface. And so that amount of flux, it has always been a concern for me, that you're removing from the solder paste that's being deposited onto the PCB.
Great. What side of the stencil, squeegee or board, do you recommend a step up when using laser welding? Is that the same for a step down?
Yeah, I would say typically we step up on the squeegee side. So the squeegee is going across, let's just say a 4 mil area, and then maybe if you've got a connector that you wanted to be 5 or 6 mils, it's a step up. What can happen is if the step is on the contact side, any components that are very close to the area that you're stepping up, the squeegee may not gasket to the PCB in that area. So that's why we typically keep the bottom of the stencil flat, and we do any step foil thickness changes on the squeegee side.
Sounds good. We see paste release issues on small apertures when the fabricator has over etched the copper. IPC says plus or minus 20% is acceptable. How does the copper pad affect the paste release?
Yes, really good question. So if you look, if I could do it, I would pull up the definition of the calculation for area ratio. But if you look at the definition of area ratio, it's the surface of the wall of the aperture versus the surface of the copper pad. So you can imagine if that copper pad is over etched, very small, let's say a very small component, then that just the over etching process is going to reduce the area ratio. So if you're calculating the area ratio based on just the theoretical size of the Gerber pads, but yet your PCB is over etched to 20%, then the area ratio could be much smaller than you calculate that it is. And that could be causing the print failures that you're seeing or paste release challenges. What we've seen in this paper that we just produced is really once we get down below 8 mil apertures, we were primarily looking at round and square apertures, not rectangular apertures. Then mass defined pads become very critical, because once these, at some point the PCB manufacturer can't hold certain sizes, like you said, there's plus or minus whatever it is, 20%. Whereas if you mass define those pads now, they can leave those pads larger, and then they can define the pads with the solder mask process. So, whether it's direct imaging or whatever process they're using, that can become a more accurate way of controlling that size. And then the other thing is you get better gasketing with a solder mask defined pad versus a copper defined pad. So the solder mask defined pad is going to gasket the stencil better, kind of create a cavity there then that the paste gets forced down into. The transfer efficiency may not be as high on a mass defined pad, but the coefficient of variation becomes very, very stable. So what we see is really small copper defined pads. There's just a lot of variation in the print process versus mass defined pads. I hope I answered that question okay.
Definitely. Let me see. We'll give it another minute to see if anyone else has any questions they want to throw in here. Where there are arrays of O402s opposite side of a BGAs or LGA, when we are experiencing a lot of tombstoning, will the U-shape aperture help?
Yes. So again, when I hear the word tombstone from a customer, the first thing I think of is excess volume. So typically when tombstoning is occurring, the challenge is, can we take away some volume to solve that issue? And then when we take away volume with tombstone challenge, we would rather take it away from the outside of the pads, like I showed earlier, versus the inside. So I would use either that rotated U shape or that rotated inverted home plate to remove paste from the outside edges, and then see if that doesn't. So you're not only removing paste from the outside of it, but you're also removing volume, right? So that 20-25% less volume can help solve that tombstone challenge there.
Great. Are there any special aperture designs to follow when using a closed print head?
So when you're using the enclosed print heads, it does kind of change the rules with step stencils. The question earlier, there's a step on the top on the squeegee side or contact side. So there's been cases with customers with an enclosed print head where we've had to put the steps on the bottom side of the stencil. As far as apertures go, I don't have as much experience with enclosed print heads, because not only is the print head closed, but it's also kind of forcing paste straight down instead of just allowing the roll of the solder paste from the squeegee to let that paste roll down and flow down into those open apertures. So so my answer is I don't have as much experience with that. I believe that the concept of using an inverted home plate to remove the concept of removing solder paste from the inside edge of an opening, for a chip component 0402, let's just say, is the same. You still want to remove solder paste from that inside edge to prevent solder balls. And again, on tombstone, you want to remove paste from the outside edge. So I think that conceptually it still should be the same. I was assuming that those solutions would still work even with an enclosed print head. Step stencils, I think the dynamics change a little bit when you get an enclosed print head. Sometimes when the blades are facing opposite of what they normally face, they could just hit that step area and just, you know, bend, or, you know, other things can happen. But as far as the home solder balls go, tombstones go, I think those solutions should stay viable.
Great. Thanks for answering all these questions, Greg.
Sure.
Well, I think we're coming up on our time here, so we'll start wrapping things up. Thanks for that presentation today, Greg, and for joining us. And thank you everyone for your attendance and participation. Just as a reminder, this webinar was recorded and you can access it through a link you'll receive in your email. As we mentioned before, don't hesitate to reach out to us with any questions we didn't get to. Be on the lookout for future topics, and we look forward to seeing you in November for the next Tech Tuesday. Have a great rest of your day.